Good day, everyone. My name is David Williams, Executive Director of the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Flexibility in Energy Systems with High Shares of Fluctuating Renewables, a German Perspective. We are grateful to our moderator, Dr. Georg Erdmann, and our distinguished panelists for today's timely discussion. We're also grateful for the support of the German affiliate of IAEE for co-branding this event with IAEE Today. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services that you can view at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please use Zoom's Q&A feature at the bottom of your Zoom window to make known your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I would like to introduce you to our moderator, Professor Dr. Georg Erdmann, former president of IAEE and professor for energy systems at the Berlin University of Technology. Georg, over to you.
Thank you, Dave, and welcome all of you to this webinar, which is organized jointly by German affiliate of the International Association of Energy Economics, GE, and of course IAEE. I am the former president of the GE and also the honorary president of the GE, which I received when I get retired some years ago. Our webinar today addresses a very important issue, namely the question how to manage electricity systems with high shares of wind and photovoltaics. And you may know that the German energy transformation was insofar successful as the German electricity system has now very high shares of these renewables already, so more than 50% in certain periods of the year. And so now the next question is, of course, how to organize the integration of these renewable energy technologies into a workable electricity market. And of course, this may be interesting for our international visitors and members, because as Germany is one of the countries with the highest, some of the highest share of renewables, we can have a field of experimentation. We can now observe what we can do and how we can do it. And our 2 presenters today, they have managed projects which had been addressing this kind of topic. Our first speaker is Markus Graebig. He is actually working with the transmission operator 50 Hertz, which is in East Germany, and East Germany is even the renewable energy share in the East German electricity system is even higher than in the rest of the country. So it's really a company which has to solve all these kind of problems which are associated there. And Markus had been just until a month ago, head of a large research project which called Windnode. And this was the idea, wind Northeast Germany. Northeast Germany has much wind and it has a high share, this wind energy has a high share of electricity consumption. So the idea was how to deal these problems, how to deal the integration of this large share of renewables so that the energy system, the electricity system is still working. He will present the findings and the results of this research project. And our second speaker is Christian Wagner. He is from a consulting company, EF Ruhr, as you can see. And he wrote a PhD thesis addressing the problem of grid expansion. If you invest into renewable energy, the question is how much renewable energy you can invest if there is no additional investment into grid. You cannot organize electricity production if the grid is not there. And Christian has developed a model that the transmission grid operator can accept more renewable energy than originally planned, simply by reorganizing the calculus and the management of the integration of renewable energy. And he will talk about this. This is the result of his PhD thesis. And of course, the idea of this webinar is so that we want to have much time for discussion. That means all the speakers both speakers will talk about 20 to 25 minutes. After the first presentation of Markus, we'll have some questions, if there are questions. And you can use for these questions the chat function of this Zoom webinar. And after the second presentation, we will have a discussion. We invite you to give comments and questions, and I hope we will have a very lively discussion. So this brings me to give the word to Markus.
Thank you very much, Georg, for that kind introduction. And you actually left out the most important part of my biography, which was being member of your team at Technische Universität Berlin before I joined Windnode. So thank you for that great time together. And in fact, Georg is part of those who brought Windnode to life back then. Okay, so I'm gonna try and share my presentation. I hope that works. Can anyone see? Georg, can you see my presentation?
Yes,
so others can probably as well.
Yeah.
Perfect. So good morning or good afternoon, everyone, depending on which side of the Atlantic you are located. As Georg already mentioned, I have had the pleasure of being the project director of one of the biggest showcase projects or lighthouse projects in Germany, for what we consider the second phase of energy transition. In fact, the challenge that we all were given by the German government was the question of what are we going to do once we approach an energy system with close to or even more than 100% of volatile renewables. In fact, they launched an R&D project with overall budget of €250 million support money, which was spent on 5 consortia. One of those was Windnode, and that was my pleasure of leading Windnode and leading that consortium for the last 4 years. Some of you, the German ones of you, are probably already familiar to the Syntec and Windnode project. The others probably aren't. So I'm going to try and give you an overview of what we have done in Windnode. What is that showcase project? And I will then try and highlight a few aspects which might be of overarching importance and interest, especially those regarding regulation, market design, and maybe also the project setup of this kind of lighthouse project. Okay. Windnode in a nutshell. Here we go. This is a map of Germany. Shows you the installations of solar and wind power plants. It's almost 2 million, more or less decentralized power plants altogether. And these 5 logos there point out the 5 consortia that I was talking about. Windnode actually is the entire east of Germany, 6 federal states. And as you can see from this map, this region is largely dominated by wind power, which actually brings completely different or quite different challenges than, for example, in the south, which is mainly driven by small-scale PV, which are connected on lower voltage levels of the grid. I already mentioned the challenge and the target, the funding. Windnode, 6 states in the east, already more than 60% renewables in the electricity mix, most of them intermittent. The TSO 50 hertz just gave out the target of reaching 100% renewables on average in 11 years from now. Wind energy prevails, and also worth mentioning, we are facing some of the most important energy transition challenges, such as grid extension from north to south, because the north is rather sparsely populated and loads are in the south. In our region is 2/3 of the lignite phase out, which has been agreed upon until 2038. So quite a couple of specific energy transition challenges here. This is just a brief overview. Don't try and memorize these logos. It's more than 70 partners who were involved, and it's basically the who is who of the East German energy business. We incorporated the entire value network, if you will, all levels of grid operators. We have energy, electricity producers, but especially a large number of electricity consumers on an industrial and commercial level, such as Siemens, Berlin Water Utilities, BMW, and others more. And that's actually the focus of our project, because we took the wind generation as a given scenario in our region, and we really focused on the question of how can we integrate these volatile renewables into the system on a consumer side mainly. Now, talking about a target of 100% renewables, I like to think and consider that question in this kind of puzzle that I highlighted on the left side of that slide. It certainly has something to do with renewable sources. It has something to do with grid extension and grids in general, smart grids, but also grid extension. Energy efficiency as a means to reduce the end energy consumption, obviously. And the aspects that we focused on were most and foremost flexibility on a consumer side. And this also interlinks with sector coupling, especially heat and mobility and energy storage. By the way, we haven't talked about hydrogen in this project, because when we started Windnode, or when we developed the project about 6 years ago, no one would have believed what importance hydrogen would gain within only a few years after. Altogether, there are 50 sub-projects in Windnode, which basically feed into this overarching target. There's also a very nice 260 pages book, which can be downloaded from our website, or I can also send you a hard copy in German or English. If you're interested, just drop me an email. That presents all these 50 projects in more detail, and I'm going to give you the bird's eye perspective, which is basically summarized in 4 fields of action. And those are the ones that I briefly want to present in the next few minutes. The first step was a technical perspective of identifying flexibility options. And the bottom line is we have found much more technical flexibility options than we actually expected. Just to give you a few examples, we worked with 4 Siemens factories in Berlin who analyzed step by step all of their production processes, put control technology into place, implemented a platform to aggregate and to manage that flexibility. We worked with the Berlin Water Utilities and Sewage Treatment, which, by the way, are amongst the biggest, if not the biggest, electricity users in Berlin. We also worked with one of the biggest supermarket chains in Germany, Lidl and Kaufland, who especially looked at the cooling sector. And if you consider there are around about 1,000 of their supermarkets in East Germany, they alone have a theoretical potential of around about 50 megawatts in refrigeration alone. we also had a couple of sector coupling projects, most of which are power to heat, some of which are also power to cold. Very big ones like Europe's biggest power to heat facility at Vattenfall, also some very decentralized ones, some very innovative ones. I like to highlight Lumenon, which is a Berlin-based startup working with steel-based high-temperature heat storage, 650 degrees Celsius, which allow to store excess electricity at a very high temperature level, and then also bring it back into a combined heat and power process if needed. So that technical level worked very well, very successful, more successful than expected. And if you're interested, I'm happy to go into more detail also about how we went about implementing these ideas with the managers in these factories, because as you can imagine, that wasn't very easy from the very beginning. Now, the second step is bringing the euro or dollar sign to these flexibility options. And as you all know, there are different marketplaces on which flexibility may have a value. For example, control power. That explicitly hasn't been the focus of this project because these marketplaces are already very well established and understood. We try to work on a, at least in Germany, non-existent marketplace for grid congestion management. 50 Hertz, the TSO in the region, together with a couple of DSOs, built up a flexibility platform, which is very, the way it works and the market processes it uses and the products it uses are very similar to what we know already from the control power platforms, plus the additional element of having locational information about where these flexibilities are. So think about Siemens or the Lidl stores or you name them. And once they understand that they have a certain flexibility reserve during a certain time span, they can offer that flexibility together with their location on that platform. It's going through or these bidders are going through an initial pre-qualification process. And once they are pre-qualified, they can offer these flexibility offerings together with a price tag. And once one of the grid operators, either transmission or distribution level, foresees a congestion situation, they can purchase flexibility from that platform in order to hopefully find a more efficient way of easing that grid congestion. Good news is the flexibility platform exists. It worked very well in all the test operations we ran. First trades have been made, but in fact, it turns out that that the regulatory framework has changed to the worse, at least in terms of the needs of this flexibility platform, especially in two respects. The first one is a regulatory amendment made under that umbrella of Redispatch 2.0, which led to the mandatory availability of generators for the regulated redispatch that was reduced from formerly 10 megawatts to 0.1 megawatt now. And that means that within the mandatory redispatch, there's a much bigger availability of flexibility options on the generation side, which in return makes it less attractive to offer flexibility on this platform. The second one is somewhere between a theoretical and practical concern about strategic bidding, known as increase-decrease gaming. That means that certain actors may have the power to artificially create a grid congestion just to earn money by then again easing that congestion situation. That concern is substantial and real. We do believe that solutions are possible, but within that project, we have come to the solution for now that the flexibility platform probably, as it stands right now, won't go into a bigger rollout. Situation may change within a couple of years to come if flexibility gains higher value. One aspect that I want to highlight is the regulatory environment of this whole project, WindNode and Syntec, because as far as I know, we have been the first project which was given the privilege of a regulatory sandbox. And regulatory sandbox means we enjoyed certain regulatory possibilities which otherwise wouldn't have been possible under the current regulatory framework. And I just brought one example out of a couple of applications of this sandbox to give you an idea of what this is all about. So one very specific aspect of German energy regulation, and this probably doesn't exist in your countries, but you may have other similar regulatory hurdles. So one of the regulatory one of the regulations is what we call Stromnetzentgeltverordnung. That's part of, or that basically says how grid fees are allocated to large consumers, and that comes with a very strong incentive for very flat load consumption. So if you look at that little spiky greenish original load curve, you can see that this remains under that annual load peak with the number 2. Because as long as a power consumer has an annual consumption of more than 10 gigawatt hours, plus they maintain at least 7,000 load hours, and that's basically just simply dividing the overall energy consumption by the annual peak load. And if that results in 7,000 or more, and the overall energy consumption in the year is more than 10 gigawatt hours, this consumer has only to pay 20% or even only 10% of the regular grid fees. So there's a very strong incentive for them to try and maintain that very flat peak profile. Now imagine we are talking to one of these power consumers and tell them, hey, wouldn't it be nice if you put flexibility into your power consumption, because this is grid friendly and system friendly and helps the energy transition and blah, blah, blah. And you will also get some support money in this R&D project. They will probably still say, yeah, well, nice idea, but I'm running the risk of overshooting my annual peak load and therefore being penalized by losing that privilege of reduced grid fees. And this is exactly the point where the regulatory sandbox came in, because the sandbox says, okay, if you're part of this R&D project, you are allowed to overshoot your annual peak load for the purpose of this R&D project, and you won't suffer any disadvantages, or more precisely, you will be reimbursed for any disadvantages that you're suffering because you are running this research project. So this isn't any windfall profit. It's really just a compensation for disadvantages you're suffering because you're part of this R&D project. And the observation we have made, and this is only one aspect out of a couple of aspects within that regulatory sandbox, but the observation that we have made is that in fact the existence of this regulatory sandbox was a much stronger incentive to participate in the project, at least for a couple of partners, than the actual governmental support money that was paid as a grant. Not for everyone, but for a couple of participants, they only came into the project because of the regulatory sandbox. And my conclusion is, if you really want to stimulate this kind of forward thinking, if you want to bring together something that makes sense on a systems level with what is possible on a business level, you have to talk about regulation, and regulatory sandboxes can be a very, very attractive and strong, very powerful catalyst, maybe even stronger than funding money. Okay, I will skip the digitalization side. Would have been worth a separate presentation, because we worked on a couple of really cool digitalization project as enablers, but also as users of energy data. Just want to mention the idea of living lab, or Reallabor in German, because we have understood this kind of R&D project not as a traditional R&D project somewhere hidden in a lab, but really out there in real life, which brings together energy transition with industrial policy, really tapping the opportunities of an innovation project. And therefore we have invented a couple of ideas. 30 visitor sites. Once Corona is over, you're more than welcome to visit here, even though WindNode has been finished now. Most of these visitor sites are still accessible, where you can really visit firsthand all these solutions that I presented, and many more. We have worked with things like energy, with literature, and much more, to try and bring the idea of energy transition into something that really is an opportunity for an industrialized country. Okay, also happy to go into more detail if you are interested. This is a summary of what we have learned. What is the idea of this new format of showcases or living lab? The official perspective of the government is that it's a third pillar besides basic research and applied R&D, and showcases have a very high TRL, technology readiness level, very close to the market, and that's basically the traditional perspective of bringing together support money with, it shouldn't be F&E Ziele, but R&D goals. Now the living lab, and that's what we've learned, brings in at least 3 more perspectives. I have already talked about regulatory sandbox. The second one is network effects, because if you have 70 partners or more, that just initiates ideas and cross-linking of expertise, which goes way beyond the initial research question. Plus the third aspect, narrative and visibility. WindNode has established connections between Germany with partners all over the world, from Japan to the US, and many of our partners have appreciated that visibility, that kind of show and tell game very much. We'll skip that one too, and being conscious of time, just want to share a few ideas of what might be coming next on the way towards 100% renewables. I have shown you the, let me go back to that very quickly. I have shown you that map of the 5 energy showcase regions in the beginning, and most of them have found follow-up projects which continue the work from these 4 years. For any W 4.0, for example, they are going massively into hydrogen. In our region, WindNode, it's really very much about the coal phase out. And if you consider the map of Germany with these 3 lignite mining regions. 2 of those, Lausitz and Mitteldeutsches Revier, are in our region, 2/3 of the German phase out. And again, keep in mind, Germany is probably the only industrialized country that undergoes a double phase out of nuclear and coal at the same time. The government has, or it's actually been a long participative process in which the target date of 2038 has been agreed upon. And for the phase out until 2038, around about 50 billion euros of total support money will be paid for these coal regions. That's a lot of money. That's round about 1 million euro per job affected. I made this this estimation. It's around about 1 million per job affected. It's a lot of money. And the interesting question is, what is going to be done with this money in order to really make the phase out something something sustainable, and also relate to that large amount of money. We have organized a conference about 1.5 years ago, just before Corona kicked in. So it was one of the last events that was still possible in person. It was in the middle of that Lausitz region, somewhere there where the 43% is put into the map. And that's in the morning of our conference. Those of you who speak German can read that sign, which was put up by some protesters there. It basically says, we don't live on green fairy tales, but on coal. And that gives you a taste of what the atmosphere is in these regions. We actually brought together a whole range of very innovative companies who presented ideas of what can be done in former coal regions. And I mean, that's a very stimulating question. I mean, what can you do with a huge, big hole in the ground, which is basically big enough to put the whole city of Cologne in there? So what can be done in former open pit coal mining regions? And during that conference, a whole range of very attractive ideas came up. This photograph, and that's my final slide, by the way, shows our final presentation to 2 of the ministers in that region. Ideas have been produced from very foreseeable ones like hydrogen, all the way down to big data centers. And I think that's one of the very attractive follow-up ideas. Why don't we bring large data centers, 200 megawatts or more, into former coal regions? There's a couple of reasons: existing power connections to the grid, usage of exhaust heat, and so on and so forth. We have been working on these ideas for 1.5 years now, just applying for funding right now, and hope to put that into a follow-up project. To finish up, 2 or 3 lessons that we have learned from the wind node project, which we believe are needed for this next step and also for follow-up projects. That's, first of all, you have to be ambitious. So energy transition needs to be understood as something like the moon landing. This comparison was made at some point. So you need to be ambitious, and you need to put management into place which also understands this as a leading innovation opportunity. Secondly, regulatory sandboxes are instrumental drivers and catalysts for this kind of forward thinking. And I have also proposed to make them part of transition regions. So we have proposed to the government to connect regulatory sandboxes to that date of 2038, instead of throwing helicopter money on the regions. Think about intelligent instruments like putting regulatory freedom in place, which stimulates certain technologies like hydrogen or other more. And finally, international networks for best practices of structural change. That's also part of what we're doing right now. I think I'm running the risk of overrunning, so I will stop here. Georg, you're still muted.
No, Markus, thank you very much for this presentation. I must say that the chat function is disabled. So if you want to ask questions, you must use the question and answer link, and then you can ask some questions. I have already some questions. Maybe some of them are more general, and we will discuss them at the end of the presentation of Christian. But there's one maybe which is really addressing your presentation. It's the question on the regulatory sandwich. Gunnar Kessler asks, he comments, regularly sandbox must go away, and the obvious need to reform the current regulatory framework results rather into an incorporation of the results from the sandbox at a wider scale level. So I understand this, that means the regulatory sandbox at the end must be transferred into regular law. Is this your idea?
My idea, Georg?
Yeah.
Yeah. That's a very good question. So first of all, regulatory sandboxes, don't get me wrong, regulatory sandboxes are just let's say a bridging element. I mean, the ideal world would be a change in regulation per se, but in reality, unfortunately, fundamental regulatory changes turn out to be very time-consuming and very challenging for obvious reasons. And just to give you one example, that is the EEG surcharge, so the feed-in surcharge in Germany, which is round about 7 euro cents per kilowatt hour, which is a massive obstacle towards the introduction of hydrogen and other sector coupling. And everyone agrees, all the academic community I know agree that the EEG surcharge needs to be abolished, and we need to implement CO2 prices. But to get that into regulation takes a very, very long time. Now, given this long time span, regulatory sandboxes can have a double effect. First of all, they can help us bridge that time span in order to continue the innovative thinking. Because if you're getting blocked by the existing regulation and you can't even develop in an R&D setting the new solutions, that would be really bad. And the second one is that you gain the opportunity of making experiences with that new regulation, at least in a somewhat protected environment. And I fully agree that at the end of this period of that regulatory sandbox, the results should be evaluated and implemented into the overall energy law and regulation. Has this been done? Well, partly. I think most colleagues from Windnode and Syntec will agree that we would have hoped for, let's say, more ambitious translation of our results from the sandbox into energy law. And I mean, the results are very obvious. I pointed out one very specific element for the grid fees. There are other elements for EEG surcharge and CO2 pricing, and some others more. Also, the opportunity to use electricity, which otherwise would have been curtailed. I would say we're somewhere in between of quarter to halfway there.
Markus, thank you. I think we go to the presentation now to Christian, and we will discuss the questions which are in the Q&A section later after the presentation of Christian. So Christian, you are ready?
Yes, most likely. I hope you can see my slides right now.
Yes.
Okay. So thank you, Georg, for having me, and hello to everybody, or good morning, depending where you are right now. I have the pleasure today to present the results of my PhD thesis, as well as the results of several projects that were done in this time work, and also that were done based on my PhD thesis and the ongoing. The title was Integration and Evaluation of Peak Curtailment. In Germany, it's called Spitzenkappung, but there is no one-to-one translation, so I did it free for the peak curtailment as a planning principle for the economic grid development in medium voltage grids. And as we already heard and Markus pointed out, the energy transition in Germany means we will have a lot of fluctuating generators, wind turbines, and solar units in the networks. And most of these units are connected to the distribution level. So the methodology is also feasible for the transmission level, but it's also feasible for the distribution level, where the most needs for the grid development will occur. And the question here is how we can integrate all these renewable energies and fluctuating generators in the networks. And the question is not, do we have to do it? But the question is how we can do it in a secure and economical manner so that it will be demand oriented. You will see on my slides the logo of my current company, the EFRUR, but the PhD thesis was done at the IE3 at TU Dortmund. But as it's the PhD thesis, as well as some further works we have done based on it, you will see both logos here. So what was the starting point? What is the point of discussion is, to integrate all these renewable energy resources, you need massive investments in the distribution grids or in all network levels, but most in the distribution levels. And I pointed out here some German newspapers and some German studies that were published in the last years. And altogether, it comes to the result, it will be really pricey to integrate all these renewable energy resources. They're speaking about 50 to 250 billion euros that are needed to invest in the networks up to the year 2050. And this is quite an amount of money. And I think it was worth to think about it, how we can do it in a more economic manner to reduce this cost and to gain some benefits. And let me start with a slide just to show you what are the challenges. In the traditional way, the grid was designed in the way that you have the loads on the lowest voltage level, and you have power plants on the highest voltage level. And then you have one directional power flow. But this changes with renewable energy sources, with the wind turbines, with solar units. So you have on the one side of volatile feed-in characteristic, and also you have bidirectional power flows. So you have the feed-in case or the reverse case. And due to this reverse case, a lot of grid expansion is needed. And also, in the future, it has to be expected that this will increase also on the load side. When we consider new loads like heat pumps, electric vehicles, there will be a huge share here in Germany, and then this goes on. So we have also the same problems on the load side. But all this leads to one thing. This is the inefficient expansion and use of the grid due to grid capacities that are rarely needed. I brought a slide here, and here you see an annual duration curve of a random wind turbine in Germany. But what you can see is that the maximum power of this wind turbine is only reached in a few hours in the year. But the way the grids are designed is that they're able to capture all the energy. So you have to design it for the peak load, especially here for the peak infeed of the turbine. So you develop a grid that is feasible to integrate all the energy, but the capacity is just needed for a few hours in the year. And this is the question, do we might have better solutions for this few hours? And we maybe can gain some benefits from it and reduce the cost for the grid expansion. So, and this question is of course not new, it was also discussed. And the German regulatory implemented a law to consider this. And this law is, I did here a free translation as it's just a German law. It's called peak curtailment or Spitzenkappung. And in this way, you are allowed to plan your distribution grid or all your grids in a manner that you assume that the forecasted energy can be curtailed by 3%. And this is also working for onshore wind turbines and photovoltaics. And to make it short, what you have to take from this is it's a tool for the network planning. So it's for the planning period, not for the operation. For the operation, you have different regulation and you have different measures, but it's already for the planning so that you don't build too many lines and too many transformers. The aim is to have a demand-oriented, economical, reasonable grid development, and it's feasible for wind turbines and photovoltaics, and you're allowed to curtail 3% of the annual energy. And if you go ahead, you can see here the curve I showed already on the slide before. In red, it's marked like what is 3% of the energy, 3% of the annual energy of a wind turbine. And you can see it's just the peak here, the peak curtailment. But when you look at the left side for the power bar, you see that it's way more than 3% in this example. It's around like 20%. And this is 20% is important for the planning of the grid and for the dimension of the grid. So what you can see here is one simply thing. When you reduce the energy by a little, you reduce the power by over proportional by a lot. And the power is responsible for the cost and for the need for grid investment. So it could be a smart idea to use flexibility in general, but here in particular, the curtailment of peak curtailment of energy to reduce the power you have to integrate in the grid and therefore reduce the network cost. Of course, you have to find other options for this time where the feed-in is. It could be curtailment. This is what I considered in my work, and this is what the law says. But of course, this is just the first step. You could use the energy however you want. So you could do it in the storage, you could make hydrogen out of it, and also you could use the flexibility of loads just to increase the load and lose this energy. But what you can see here is like the basic the principle. With a little energy loss, you can reduce the maximum power by a lot and therefore reduce the need for grid investment. And this is what the law already intended, but there were no concrete legal requirements for the implementation of this peak curtailment. So basically there was a law, but there was no way how to do it, like how to get benefit out of it. Of course, there were several studies and there were several projects, but they didn't consider the concrete legal framework, and also they didn't do it on a large scale. They did it just exemplarily. And this is where my PhD thesis came to play. I said, okay, there's a lot of work around this topic and there's a regulation right now, but there's the gap somehow to combine all of this and see, okay, what is the impact of this curtailment? What can I gain from it? And also, is it economic or is it not economic? And based on this, there were 3 questions derived. First of all, how can the peak curtailment implemented? So what are the different ways? And how can it be implemented in the established planning process of distribution grids? And the second part is quite important because you can make a model on a scientific way to show that it works. And I did, and I showed it works. But the next step is to go a step further to make it that way that it can be already implemented in today's planning so that you can make use of it in the practical. And I can say it is used in Germany right now to get benefit of it. But this was also like a key question of my thesis, how can it be used in the established planning process? And then the second question is, okay, what is the technical gain out of it? So how much I can increase the grid hosting capacity? So how many more DGs I can integrate in my system by using this peak curtailment? And the last question is, the question was also raised in the Q&A question, do we always need an economic incentive? And my answer is quite simple, yes, we do. Otherwise, people won't do it. And the question was, is it economic to do peak curtailment? Or like, what are the savings or are there any? This is a question I will focus today on and give you the results. Due to the time, I will not go into detail for the methodology. Of course, I will be happy if you have any questions to answer them later, but I will focus on the results to give you the knowledge I obtained doing this analysis. And on the second part, it will be just like one Outlook slide. I will show what we did afterwards. At the EFO, my current company I'm working for, we transferred this methodology to the load side, especially to electric vehicles, because we expect in Germany that there will be also a lot of needs for grid investments due to electric vehicles. And we transferred this methodology, and without giving too many results right now, I can say it's usable there, and it also has a high gain to do it. But once again, it's just the first step. In the end, we need to coordinate it and jointly optimize use of all this flexibility. But yeah, we will see it. So how can peak curtailment in distribution network planning be integrated? And there are basically two ways. Of course, there are several detailed ways you can do it, but basically can always broke down to these two ways. I brought here a really simple example to show you the principle. Shown is the generation in the load for 7 random picked hours on a distribution level. And you see the dashed line that indicates the maximum power that the grid is feasible to capture. So when this maximum power is reached and it goes further, the grid is overloaded and some action has to be done. And what you can do now is you can do the curtailment either in a static way. So that means you do it quite simple. You only look at the generation, and whenever the generation is higher than the grid capacity, you do some curtailment, here indicated with the red line, with the red bars. So whenever the generation is higher than this Pmax value, you do some curtailment, and therefore you ensure that your grid is not overloaded. The positive way of doing this is it's quite simple, it's easy to integrate, and you just have to see your generation. The negative way is, or the downside is, you can see already here in the darker bars, when you consider the residual load, so taking also the load into consideration, you see you do either too much curtailment, or you also curtail in hours where you actually have no overloading due to the grid, as load and generation are neglecting each other. So to address this, you can do it also in a, let's say, more smart way. It's called the dynamic curtailment. And therefore, you don't look only at the generation, but also at the load and the actual grid loading. So what you actually do is you just curtail when considering the generation and the load. And then you have a overloading of a line, or you have a voltage issue or something, then you just curtail as much as is needed to solve this problem. And this is, of course, way more efficient, but it's also more complex because you have to consider the load, you have to consider generation, so you have to have this news. Also, you have to consider the actual grid loading, which is a nonlinear system. So it's quite difficult to do it in an optimized way, as you have to do it on a yearly basis and optimize it for all plants in the network, as no unit is allowed to lose more than 3% of the energy. But as always, there are places where the simple approach is more beneficial, and there are places where the more complex approach is more efficient. And I did the testing and I checked it, and I will show you the results later on. But first of all, I will show how I did it. For the static curtailment, it's, as I already said, the more simple approach. What I did is, like, I considered over 1,350 measured time series from power plants, PV and wind. I had 1,350 from each of different years and different locations in Germany. I did a statistic analysis to indicate how much you can reduce the relevant power for the distribution network planning in order to not lose more than 3% of the annual energy. And I will not go more into detail here. Also will not go more into detail for the dynamic curtailment, just saying that this is a mathematical optimization model. Basically, it's a security constrained optimal power flow problem, where you have to ensure that you don't have violations of the grid constraints and you don't curtail more energy than 3% of any unit in the network. And also you have to consider that you minimize the amount of energy you curtail by using the sensitivities in the network. But you can perform this, and therefore you can gain the additional benefit of the dynamic approach, but you have to have the expression, you have to have the data and the measure of the network. So, but what we can keep in mind for now is you have two ways to do peak curtailment. One is the static curtailment, and the other one is the dynamic curtailment. So The question is now, if I do curtailment, what is the benefit? So, and I did it in a technical way to address the grid hosting capacity through peak curtailment. So the question, how much more renewable energies I can integrate in my grid by using this peak curtailment. And first of all, you have to know distribution networks are very heterogeneous. So you have a lot of different distribution networks in Germany. Like we have in the medium voltage, it's around 500,000 networks we have. And of course, everything is different, but some are in some groups are similar. But it's not sufficient just to look at one grid and based on this drives the results, because you can get a grid where the effect is quite good and you can have a grid where the effect is quite bad. But the question here is, if you want to do it on a large scale in whole Germany, what is the impact? So you needed to do it for more than one distribution grid, of course. Then you have to consider when you go into the planning of a distribution network, you use some lines, you use some transformers. So every distribution grid has quite of a reserve. So before you have to do any measures to extend your grid, you can install a few you can install a few new more renewable energies into the system, a few wind turbines, a few solar panels, whatever. And this is different for all grids. So if you want to see what is the impact of peak curtailment, you have to you are not allowed to take this reserve into account because it will not give a fair result. And the last one, what you have to keep in account is that the measures that are needed to extend your grid are different for different distribution grids. It's shown here. It's a figure, like it's a really basic figure, but it shows quite. You have some reserve. You can install more wind turbines to your network. Then you have to do one expansion measure, for example, exchange transformer, and then you can extend a lot of more units before you have to do the next measure. And when you do it for different distribution grids, it will be a different shape. So at some point you have to do, first of all, you have to do different measures and you have to do it as a different time. So what I did is I used the model to integrate the distribution units in the network until there is no reserve left. Then I used the static and the dynamic curtailment and checked how much additional grid capacity I gained by doing this. And as I already mentioned, it's not enough to do it for one grid. So I did it for 120 grids from different regions, presenting real distribution grids in Germany and to derive the results. And of course, therefore was an automated simulation approach needed, which I also developed. As I mentioned earlier, due to the time, I will not go into detail with the methodology. I will go directly to the results. And here you can see what is gained by curtailment. It starts at 100% because I already mentioned that we consider the networks will have no reserve. We extended it further that there is no reserve. And here you can see what additional grid costing capacity could be gained by using peak curtailment. In the gray bar, you see the static approach, and in the green bar, you see the dynamic approach. And those bars are overlapping because the dynamic approach is per definition more efficient than the static approach. And without to go too much into detail for a single network, what you can see here is that you can gain a lot of grid hosting capacity by using peak curtailment. It was around 30% in average when you do it for the static approach, and it's around 50% when you do it the more complex dynamic approach. What you also can see is that for single or individual grids, the benefit is way higher. So it's a huge benefit you can gain. On the other hand, there are grids where the benefit is around like 20%. So not so much, but still you have a benefit. So what you can take from this is like, first of all, peak curtailment seems to be a technical good measure to increase the grid hosting capacity. And also if you do it not in general, but then when it's quite efficient, then you can gain way more, like 100% or even more. So it's a quite efficient measure. But of course, it's just one option of all options you have. So the economic perspective is quite important to see if I do it in an economic manner. But what you can see here is like, from the feeling, it should be economic. because you can integrate more renewable energies in the system without expanding the grid and have investment for expanding the grid. Of course, you lose at maximum 3% of the energy, but if you can integrate like 150% of the power of renewable energies and all of this 150% power infeed 97% of the energy, you will end up by 145% of energy. So a quite huge increasement of renewable energy in the system without doing any investment. So what I did is, in the next step, I did a project at this time, and we used a study case of a German federal state to see if we use peak curtailment in this federal state, what will be the impact of the grid development and the need of investment for the networks. And therefore, two models were needed. First of all, you have to think you need a reference case. So the reference case was you do grid expansion the traditional way. So you put additional line, you put additional transformers, you do reconfiguration of the grid and so on. And therefore we developed the model that do it automatically, because I already said we don't do it for one grid, but we do it like for a huge share for 120 grids to see what is the impact. And then the result of this model is the investment for network reinforcement. And this model is also able to consider the peak curtailment. But what you also have to consider when you do peak curtailment, the energy is not free, the curtailed energy. You have to compensate it. Like in Germany, by regulation, there's a law that you have, like to make it simple, you have to pay the same amount as if the energy was used. But now, this is a tricky part of the German regulation. There's a difference between how you consider curtailment in planning and how you consider curtailment in operation. So the approach of peak curtailment is 3% per plant per year. But in operation, it's quite different, because in the operation, you have more options. You have the OLTC, the transformers. You can use the transformer tab to solve voltage problems. In this case, you don't even have to curtail. You also have the queue management of the distributed generators. The common way in Germany in the medium voltage to do it is the queue for new control. There are, of course, different measures, but you can do it, and you do it. So, and only if all these measures fails or not sufficient, you do the curtailment. So in the practical, in the operational way, you curtail more than 3% of the energy. We also did this investigation, and I presented this in my PhD. I will not go into detail for this, but what you can keep in mind is that curtailment in the operation is the last option. And if you assume you curtail 3% in the planning, in the operation, it will be even less. So, however, the curtailed energy has a value, and this has to be compensated. And when you do the comparison between the traditional grid reinforcement and the approach where you already also consider peak curtailment, you have to take this into account. So I will go directly to the results. The absolute level of investment here is not so important. What is important to know is the relative share. So what we did is we investigated how much investment is needed in the medium voltage level to extend the whole grid in the German federal state Baden-Württemberg for the year 2030. And what you can see is both ways, the static and dynamic curtailment are able to reduce the cost by a lot. Like it's around 18 to 20, 22, 23%. Of course, this is just one example, but this example is representative, as it's done by, it's arrived by a lot of grids. And it's also in this way representative that when you look at whole Germany, the numbers will change a little, but the overall statement will stay the same. So the savings are quite a lot. They are over 20%. What you can see here is, of course, it's shown in the black. You have some savings in the grid extension by not have to build lines and not have to build transformers, but you have to pay for the compensated energy. You have to compensate for the energy that's shown here in the black. And also there are cases where it's more expensive to compensate the energy than the assets you save. This is shown here in the gray bar. And in this case, you simply just make the traditional grid reinforcement. But what you can get from here is the peak curtailment is a quite efficient measure to reduce the cost for grid reinforcement and also to increase the share of renewable energies in the system. So it's really quite beneficial. Okay. To sum it up and also to say what you can learn from this and how you can take it further is, first of all, we show the implementation of peak curtailment can be done in a static and a dynamic way. And we show that the technical benefit is quite huge. The grid hosting capacity gains through to static and especially the dynamic peak curtailment is huge. And the added value of the dynamic approach is given, but it's not given in all grids, so it's part dependent. And this is also a point I have to point out from the slide before. The savings I showed were not achieved in the majority of the grids, but in around like 10 to 15% of the grids where peak curtailment is quite efficient. So for the individual grids, the savings were way higher, but overall you can see if you do peak curtailment in the grids where it's beneficial, it's overall beneficial because the savings are quite high. So what we did in the next step, and this is the part what was done after my PhD, is we learned that the curtailment or the peak shaving in general is an efficient measure to reduce the need for investment in the distribution grid or in general in the electric grid. So in the future, when we expect there will be a high share of electric vehicle and there will be a lot of heat pumps, we will face basically the same challenges. We will have a high peak load due to the simultaneity of these units, but this high peak load will not be in all hours, but only in a few hours. For example, just to make it simple, when everyone comes home from work, he puts his charger in his electric car, and then you will see a high grid load. And here, once again, you can see that the flexibility is a key. So what we did is we derived this methodology also for loads to see what will be the impact. And the impact is also huge as it is on the generation side. And of course, it's not that you have to curtail it by any means. You could also shift it, or you could also use storages. You can use it to make hydrogen or gas or anything. But the key finding is it's quite efficient to curtail or save or store or shift these peaks. And it's also technical and economically beneficial. So I just made here one slide. I showed also some results. They will be published soon. But what we do now with the methodology is like we consider how new loads can be implemented in the planning approach in general. How can control schemes, operation strategies be performed? How you can optimize the system, and based on this, are there and which are the business models? Of course, hydrogen and sector coupling is a huge topic in this field. I already pointed out a few times, because you see the benefit just from curtailing the energy is so huge. And when you then start not to curtail the energy, but use it in a different way, it could be even further. Yeah. So this was just a few highlight what we do based on these results. But as I already said, I wanted to focus on the results on the generation side. And if you have any questions, feel free to ask, and I will be happy to answer it. Thank you.
Thank you, Christian. I think our two presentations have shown three things. First, it is possible to integrate renewable energy or non-dispatchable energy at easier and at lower cost and more efficiently than originally expected, simply because we use our intelligence, our research results, and this helps to expand renewable energy or to develop the energy transformation. Second conclusion is regulation is crucial, and it is still not quite clear how regulation is made right. I think particularly Markus gave us examples that regulations is very important, but also Christian showed us how important regulation is for creating a renewable energy system at reasonable cost. And the third thing is, of course, as a professor, as a former professor and research specialist, I think it is our two presentations shown that the results of research have an impact in real life in the energy industry, and this shows that activities that we are doing in IEE and in other research communities are important. I think these are really findings, and I think the highlights of this session. But now we have a lot of questions. Christian, maybe my first question is, can you give us examples where your model has been applied in distribution grid networks?
Yes, I can. First of all, it was used for the, it's called, there's, let me say it in a different way. There's different DSOs that are already using the peak curtailment. For example, one is EWE, which is in the northern part of Germany, a large one. There's also one in the south. It's called Bayernwerk AG. They are using it. Of course, they are not using one-to-one my model, but I was in a working group with them where I developed some of these approaches, and they use it for their specific time series. So the results are a little bit different, but they're using it there. And these are two examples of the largest DSO in Germany. It's also used in several studies for the German government. And based on these studies, their particular decisions are made. For example, like this, to mention the law for the loading of electric vehicle, where the shifting and curtailment is also considered.
Well, thank you very much. Now I come to our question and answer. There are many questions and answers, and I will probably skip those questions which are very focused on the German situation. Let us discuss more the international aspects of this research. And there's one question, probably to Christian, with the assumption that the energy transition will incur in a further rising demand for network capacity, is it wise to start with peak curtailment now, or should we develop the grids today when we are able to have more renewable energy? This is, I think, a very clever question, and this question comes also from Paul Griesberts. Why not apply Redispatch? No. What if grid expansion is anyhow needed? Are the benefits then similar? That means maybe today we stop investing into distribution grids, but sooner or later we need more distribution grids. What is your answer to these questions?
Yeah, thank you for the question. It's a quite good question, but also a question I know because it comes quite often when I present my results. Curtailment and grid reinforcement is not either or. It's something that goes together. As I pointed out in my example, I have to do traditional grid reinforcement in around 85% of the networks. And even in the networks where I did the pre-curtailment, it's not that I only do pre-curtailment, I also do grid reinforcement. So it's a combination, but it makes sense to start with it right now, because on the long term, you will have a system otherwise that is designed for, it's called in the German, for the last kilowatt hours, or how you can say it, like for the last unit in the network. So at some point you have to start to consider this, and it always makes sense to do it right now, because it's not that when you do curtailment right now that you cannot reinforce your grid any further. You can do it also in 10 years. This is also an additional benefit you get from curtailment, because today, when you have a congestion in your grid and you have to do reinforcement, to which extent you do the reinforcement? Like, it could be sufficient until you have your target system, but it could be also just sufficient for 2 years, and then you have to do reinforcement again. And with the curtailment, you get two options, two benefits. The first is you gain time, so you can do the curtailment in a short period to see how your grid develops, and then based on this, do the right measure. And also you can do it in addition. For example, when you see, okay, my transformer will be overloaded by a lot, then of course I will exchange it. When you know my transformer's lifetime will end in around 5 years, and then I have to exchange it anyway, you can do curtailment to wait this 5 years to see how your grid develops then, and then exchange the transformer because you have to exchange it anyway, and you know which size you need. Also, when you need an additional line, but like grid expansion is like deterministic. Like either your grid is overloaded or it's not overloaded. But when it's overloaded just by 2 or 3%, you have to install an additional line to solve this overloading. And in this case, curtailment could be a huge option because you don't have to install this additional line. You just have to curtail for a few hours in the year when your line will be overloaded and you are done. So it's not either or, it's always a combination. And if you need grid expansion anyway, that was the second question, it still makes sense to do the curtailment. Not in general and not for each particular grid, but for the overall grid, it makes sense to look in which cases curtailment can be beneficial. And there you do it, and there you gain a lot. And as I pointed out 2 times already, in my investigation, it was in around 10 to 15% of the grids the case, and you could still save overall 20% of the investment. So which is quite huge in my opinion.
Thank you very much. We have another question in the same direction. Why not to apply the redispatch instead of peak curtailment?
Okay, thank you for this question. Here I can give a split answer. First of all, when I did my PhD, Redispatch 2.0 was not on the line, so there were no option for Redispatch in the distribution level. To go content-wise, the curtailment, a Redispatch or dispatching is an operational measure. Here we're speaking about the planning period. So however you do it, if you do a dispatch or redispatch, you still have to have a way to consider it in the planning. And this is what I did here. So I considered 3% of the energy will be curtailed. And this is the benefit we gain from it. But you can use the same methodology, you can use the same approach, and you will get the same results when you do something different with the 3% energy. You can store it, you can also dispatch it. But when you have a congestion in your distribution level, then due to renewable energies, then you have to curtail the energy in any way. So even if you dispatch somewhere else in the grid another plant, you still have to curtail this energy to get rid of the congestion. So basically there's no different option besides storage or use the energy by loads or whatever.
Thank you very much. Excuse me, Markus.
Maybe to add another question, I find these results very intuitive and very convincing. Now the question is, how do we get that implemented? Or let me rephrase that question: why isn't that being done in the planning process right now? And it seems to me that this has to do with regulation, particularly with what we call incentive regulation, because what triggers investments of grid operators, and it's basically putting hardware into place. So if a grid operator wants to develop a smarter way of operating the system, of avoiding certain measures or such, it is the question is, does their incentive model really give any legroom for that? And I think to a large extent it doesn't. So we may also need to ask the question, what needs to be done regulation-wise to allow for these smarter ways of peak curtailment to be put into place. A second aspect might be mindset and beliefs, because we are still largely triggered by certain beliefs like energy efficiency. I've often had that discussion of what does energy efficiency mean in times of surplus energy, where we're actually curtailing and throwing away green energy. So the whole established concept of energy efficiency becomes obsolete. But these, let's say, obsolete ideas of energy transition might be still playing into concepts of using curtailed power. And there's been a long discussion about use instead of curtailment. For example, the 2 or 3%, and it is around 2%, which is currently being curtailed. So the practical curtailment is pretty close to that number of 3%. And the discussion has been, how can we make that power which is otherwise being thrown away accessible, for example, in power to heat models. And again, that brings me back to regulation. It's simply not possible from a regulatory side right now.
Thank you very much. I think the key problem for the grid operators, they are monopolists. And of course, the incentive for them to be economical is of course smaller than if you are in a competitive situation. And of course, there's a lot of theoretical discussion about how to regulate a monopolist, a lot of ideas, but the reality is it really the regulators, the German regulator or the other regulators around the world, are they really doing an efficient job in such a way that they really try to find out all the saving potentials, which, for example, Christian has shown us. I think this is a theoretical question, and maybe we have not so much time, I think, but we have two, let us say, more philosophical questions from Gunnar Kessler. The first question is, has the energy transition only a chance if we are able to put a dollar or an oil-euro label on everything? Or put as another question, does everything actually need to be business modeled? I think this is a very fundamental question. The energy transformation will not come by itself, but only by financial incentives. What are your statements? Maybe Markus?
That's really, it seems to be an easy one, but I think that's a very difficult question. And I would say yes and no to the dollar and euro sign. So for a long time, I would have said, obviously it needs to have a dollar or euro sign, because that's how economic entities work. And I still believe that this is right to a large extent. If you want to incentivize companies or any other business-driven entities, money is the central optimization target. And I think it really, in that sense, it really comes to the question of getting the rules of the game right. You need to make sure that the euro and the dollar sign optimizes the individuals in the same direction that you want to optimize the system. And as long as we have that paradox situation of having rules implemented, like, for example, you don't pay for CO2 emissions in many sectors, but you do pay a surcharge on green electricity, that's obviously pretty strange, and you need to make sure that regulation points into the same direction, or aligns basically what makes sense from a systems level and what makes sense from business level. So therefore, to a large extent, yes, there needs to be a euro and a dollar sign with the right rules of the game. But I do also believe that we are starting to learn that there might be aspects to what we have formerly considered a pure commodity, like energy, that there might be aspects to it which go beyond euro and dollar signs. And one of the first time that I came across that thought was about 8 years ago at TU Berlin, when I did a study about battery storage systems, like private battery storage systems, which back then didn't make sense economically. There simply wasn't a business case to them. If you simply considered what advantage would an individual have by putting this home storage system in place versus just getting power from the power line. And still people did it for reasons beyond euro and dollar, because they enjoyed that independence, or because they enjoyed that aspect of technological innovation and being, cutting edge with what they have in their houses and so on. And over the time, I've come across a couple of these aspects also during the Windnode project, when we started working with rather unconventional measures like also arts and such, art and literature. And suddenly you come across ideas where you may develop the story beyond the commodity story. And that's actually not what we are used to as energy economists. So I don't really have a very informed opinion on that, but I do have at least the feeling or hypothesis that in certain parts of the energy value system, there might be the potential to go beyond euro and dollar sign. But I haven't really solved that tricky question yet, to be honest.
But for our visitors, Markus is known as an expert for energy and art. So it is probably his sub-project which he likes most in Windnode. And if you read his documents from the Windnode, you will see the result of energy and art research in this development. I have another question from Claudia Esser-Scherbeck, which is probably addressing the work of Christian. You are talking about flexibility for grids. Flexibility is also needed for the integration of renewables directly into the sales portfolios. That means trading. What do you think about this competition situation for flexibility? That is the old question. Should we use the flexibility for trading or for the grid?
Yeah, thank you for the question. I will not be able to give the ultimate answer to this because I think there's simply not right or wrong answer. And first of all, there's always a conflict with the flexibility, not only between different markets, here shown as the grid and the peer-to-peer, but also within the grid. Like you can use flexibility only at one level. So if you use it at distribution level, you cannot use it at transmission level. What I do think is that the curtailment is a good measure to be used for the grid. But flexibility in general will be, the huge part not be used like in the grid-oriented way. So it will be not used to reduce the cost of grid reinforcement. You need to have a grid that is able to transfer the energy that is needed, because somehow the grid is a limitation for the market. But it's not the way that the market should serve the grid, but the grid should serve the market. But there are limits. You cannot extend the grid in the way that you can do everything you want in the market, because it will be on the global perspective, not economic. So to give you the most precise answer I can give you, like I think curtailment is the option for the grid in the most parts, but the grid will have to reinforce to state that most of the markets can act in the way they need to do. You can also see it on the flow-based trading between the regions, as the market coupling flow-based. I can just repeat it to make it short. Some potential of flexibility will be used at the market. Curtailment will be used in the huge way for the network. But the network will have to serve the market and not the market, the network.
Thank you very much. I think I should stop now the discussion. Still, we have a lot of questions, and I will ask Rebecca, can you store the questions so that we send this question to the two speakers, and if they are able to answer them directly to those who have asked them?
Absolutely.
Absolutely. So that is fine. So that means if the questions which have not been answered, there are a lot of questions which have not been answered, maybe we will try, or the two speakers will try to answer them. This brings me to the end, and I would like to thank you very much for the two speakers, brilliant explanation of their speeches, of their work. And thank you also for IAE to give us the opportunity to present this kind of research and this kind of project results. And I will give back the floor to Dave.
IAEE wishes to thank Dr. Georg Erdmann and our distinguished panelists for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.